Good afternoon and welcome to this distinguished lecture. And apologies for the 4 minutes delay because of the heavy traffic jam. Today the lecture will be delivered by one of the renowned number theorists, Professor Michel Waldschmidt. Professor Michel is currently professor at Sorbonne University, France. He was awarded PhD from Bordeaux University in 1972. He has about 25 research students and more than 200 publications in reputed journals. He is a member of Commission for Developing Countries, CDC, of International Mathematical Union. He is former president of European Mathematical Society. He is serving as a member of editorial boards of many reputed journals, including Journal of Indian Mathematical Society, Hardy-Ramanujan Journal. Among the many distinctions and awards he received, the latest is American Mathematical Society Bertrand Russell Prize in 2021. He is a member of European Mathematical Society, American Mathematical Society, Ramanujan Mathematical Society, Indian Mathematical Society, and many more. He is involved in popularization of mathematics, especially cooperation in mathematics between France and several other countries. He visited about 80 different countries and delivered lectures in most of them. This year, he started his visit to India on November 14th. He reached Cochin after giving talks in many institutions in Mumbai on November 18th and will be here in Cochin until November 20th. He will be in India until 7th December. We are honored to have a well-known, remarkable mathematician, Professor Michel Waldschmidt, here to deliver the distinguished lecture. And I thank him for finding time to spend some time here in spite of his busy schedule. I thank Dr. A. Vijay Kumar, Professor Emeritus, Department of Mathematics, Cochin University, for his support in getting Professor Michel to deliver this talk. With due respect, may I invite Professor Michel to deliver the talk and request him to talk on square root of 2, the golden ratio, and the Fibonacci sequence. Professor Michel, please.
Thank you very much for your kind words and for your introduction and for welcoming me here. And thank you to Professor Vijay Kumar, an old friend of mine who organized, who started this idea, which I immediately said yes without any hesitation, even if my schedule is a bit tight. It's always a pleasure for me to meet people and to explain the mathematics which I like, and to share my knowledge and my passion for mathematics. So thank you for coming. Today I chose the topic which is the square root of 2, the golden ratio, and the Fibonacci number sequence. This is a classical topic, but I will try to say a few things rather new. Maybe the light could be, yeah, excellent. Yeah, I think it's better like this, isn't it? Yes. So I will speak of the square root of 2, which is a real number which starts with 1, and then you have an infinite decimal expansion. Infinite because it's an irrational number. The same for the golden ratio. So there are 2 irrational numbers, and I will say a few of their properties. The golden ratio is closely related with the Fibonacci sequence, and I will say a few words about this well-known sequence. The square root of 2 occurs in the Babylonian tablet, which was 1700 roughly before our era. And it occurs with accurate sexagesimal approximation. Sexagesimal means that it is in basic 60, which was the way they used the numbers. So instead of writing 414, which is the decimal expansion, they wrote in the 60, this is 60, and so they wrote 1. So this is the translation of what is written here. 1 plus 24 divided by 60 plus 51 divided by 60 squared plus 10 divided by 60 cubed. And it's quite remarkable because it's accurate for 6 decimal digits. 1, 4, 1, 4, 2, 1, and then it should be 3, but it is 2 and then 9. So it's very interesting to see that they were able to compute this number to such an accuracy. So to explain where the number square root of 2 occurs, I will start with something that you know well, which is a piece of paper. And if you take a piece of paper, a classical one, you usually have a paper which is the A4 format. What is A4? I will tell you a little bit more about that. But it is an international standard, which has the norm ISO 216. And in centimeters, it is 297 centimeters on one side and 210 in the other side. The ratio is 99 divided by 70, which you obtain by simplifying by 3. And you see that it is accurate for the decimals 4, 1, 4, 2, and then the next one is 8, while it should be 1. But it's very accurate, so it's a very good approximation of the square root of 2. So this is the standard, the norm, and this occurs for the following reason. This is a rectangle which has 2 sides, and if you say that one side is 1, the other side you define it by x, and the property is the following. We will say that the proportion is x divided by 1, and you have the following property. If you take an A4 paper and you cut it in 2 parts, you fold it in the middle like this, you have a smaller rectangle. The smaller rectangle has one side, the long one, which is 1, and the small one, which is x divided by 2. So the new rectangle that you have has a proportion, which is 1 divided by x divided by 2, which is the same as 2 divided by x. And the choice of x equals square root of 2 is done in such a way that the small rectangle has the same proportion as the big rectangle. So how to check that the 2 rectangles have the same proportion, the same ratio? What you do for that? If you have 2 rectangles, if you want to know whether the ratio is square root of 2, you look at them like this, and the small rectangle will just hide the large one. If the proportion is not square root of 2, it will not work. If the proportion is square root of 2, or roughly square root of 2, up to what you can see with your eyes. You can say it in another way. So this is what I just explained with the large A4 paper, and this is the smaller paper, and we will see that this is the A5 paper if you fold it by 2. Another way to say it is to say that if you put the small one, the corner, left-hand corner of the large one, then the 2 corners here are in a straight line. This is the picture which is here. You have the large A4 paper, you have the small one, and then the 3.0 C and C prime are on the same line. And if you reference in a paper which is in French, so the first point is that it is in French, but probably there is something similar in English. The second point is that the reference is so small that you cannot read it, but it does not matter because this file is on my website, and so you can just download it and get the references. So the number square root of 2 is twice its inverse. Square root of 2 is the same as 2 divided by square root of 2. This is the property that just occurs for the A4 paper. So the definition of the A4 paper is the following. If you put two A4 paper one next to the other, so if you double the side, which is the small side, you have the paper which is A3. So A3 is the double of A4. And then when you double, you have A2, A1, and A0. So A0 is the large one, A1 is this one, A2 is this one, A3 is this one, and A4 is just the small one. The definition is that A0 has an area of 1 square meter. And so this gives the definition of the ISO norm. There are some other formats which are not so well known, but which are used. One is the B format and the other is the C format. The B format, again, has the same proportion, square root of 2, but it starts with B0, where the small side is 1 meter. And the long side, of course, is 1.414 meter. So B0 is a very large piece of paper. C0 is different because C0 does not, the proportion is not square root of 2. The sides are 1 over 8 root of 2 and 8 root of 2, which gives this value which is here. Maybe you have seen these numbers 141, 119, and 84 and 71 when you use a Xerox machine and you want to enlarge or reduce some paper when you Xerox, because these numbers have been chosen since they are approximation of square root of 2, fourth root of 2, 1 over fourth root of 2, and 1 over square root of 2. This is very convenient to have this proportion because when you enlarge or reduce, you do not lose some information. You get really the same thing. Very often I see some pictures which are done where the people do not respect the proportion, and then the photo of the people are either very slim or very fat, and it's important to observe the proportion. So for the format A0, A1, A2 in centimeters, you have this approximation when these values, which gives the size starting with A0, and then the A4 is 29.7 and 21, approximately. So I mentioned the fact that square root of 2 is an irrational number, and often some students tell me, I know the proof. And I told them, oh no, this is not true. You know one proof, but there are many proofs of the irrationality of square root of 2. The proof that you may know the best is to write square root of 2 as a quotient of 2 integers and say that one of them is odd and the other may be even or odd, but one at least is odd. And then by using the divisibility by 2, you get a contradiction. But there are many other proofs. And I would like to explain a little bit some other proofs in the following way. I told you that if you take a paper which has the proportion which is square root of 2, then if you cut this paper in 2 parts, you have the 3 corners which are on the straight line. I told you that before. So it means that you have rectangle. One side is A, so this is A, and the other side is B. And you have the quotient B over A, which is square root of 2. So you have one side A, this side here, and the other, well, okay, you have A and B, which is here. So this is the small rectangle, and the large one is A and 2B. Because you have split it in 2. So the point is that A divided by B is the same as 2B divided by A. Because when you fold in 2 parts, you have the same proportion. So if you look at the number A prime that you have here, it is 2B minus A. If you look at the number A prime, so this was A prime. If you look at B prime is A minus B. B is this one. And so you have A prime equal 2B minus A, B prime equal A minus 2B, and since the proportion is the same, you have A squared equal 2B squared, and A prime squared equal 2B prime squared. But A prime is less than A, B prime is less than B, and so if you start with A and B, which are the minimal solution of square root of 2 equal A over B, then you get a smaller solution with A prime and B prime, which are smaller, and you know that you do not have a decreasing sequence of positive integer, which is infinite. So the process has to stop, and this proves that the square root of 2 cannot be written as a quotient of 2 integers. I will explain a similar proof of the irrationality of square root of 2 in a geometric way. Assume A squared is equal to 2B squared. And so you have one green square and two yellow squares. And you have the property that the area of the green square is the same as the sum of the area of the yellow squares. And now you have some painting. Say that you have some yellow painting. And what you do is that you put the two small squares inside the green square, that they will overlap. So there is a part where they overlap, which is the red part, and there is a part that they do not cover, which is the green part. So you start painting this picture in yellow. And so you paint this yellow part and this yellow part. You do not paint now the green and the red. So you have some painting which is left. What can you do with the painting which is left? What you can do is to paint the red area. So you can paint the two yellow ones. So if you paint the two yellow ones, you paint the green area, the red area twice. Because you can paint this one and this one, so the red area, you paint it twice. And for the green area, you have the part which is here. And so it's the green area that the area of the green, the sum of the two green ones will be equal to the red one. And so you have again some smaller squares, the red and the green, which have the property that the area of the red is the same as the area of the two green. So you have a smaller solution, and again, this is not possible with integers. If you start with squares with integer squares, the size, it is not possible. I will give a similar proof of the irrationality of the square root of 3. I can tell you that I do not know a proof for the irrationality of any square root of an integer, but it works for 2 and for 3. For 3, the proof is the following. I do it again with a painting. You have a big triangle which has an area which is the sum of the areas of the three small triangles. They are all equilateral triangles. So the big triangle has an area which is A squared, and the small ones have an area which is B squared, each of them. And you assume that the area is the same. So A squared is 3B squared. Now you have some painting, you paint the red part, and some painting is remaining. You can choose, either you paint the purple, the three purple small triangles, or you paint the white, which is in the middle. Which means that the white triangle has an area which is 3 times the area of the small one. And again, if you do it with integers, you see that you start with integers A and B, and the side that you have are again integers A prime and B prime, and the argument is the same. You have a sequence of integers which is decreasing, and this cannot be infinite. So you start with the smallest A and B, and then you see that you cannot go further. The fact that the square root of 3 is an irrational number, which I just proved, has an interesting consequence, which is that there is no equilateral triangle. So I have put in small letters on the screen of the computer. If you have the screen of the computer, if you consider that it's an ideal screen, with each pixel which is a point in the mathematical sense, so just a dot without any surface, then if you want to construct an equilateral triangle, you will find, you will put the extremity of the triangle on the network, on the grid. You have a grid which corresponds to the pixel, and so each summit, each vertex of the triangle will be on this grid. And so, if you look at the triangle that you have here, if you put the triangle on the screen of a computer like this, then the area of this triangle will be a rational number. And the reason is the following. You look at each of the three triangles which are here. The sides are integers. Integers mean that they differ by an integer number of the pixel. This is the in fact, it will be half an integer, but it's a rational number, because it is the product of this number by this number divided by 2 for this triangle here. Here, it's also half an integer, and this is also half an integer. So the area of the blue part is a rational number, and the area of the square is an integer, and therefore this triangle has an area which is rational. Now assume that you start with a triangle which is equilateral. When you look at a square is the sum of two square integers, so a square is an integer. Now, if you look at the area of this triangle, it is the product of h by a divided by 2. Well, so yes, it's half of h times a, so h times a divided by 2. So when you look at this product ha divided by 2, you have to look at what is h. H squared plus a squared divided by 4 is a4. So h squared is 3/4 of a4. H squared. So h is the square root of 3 times a divided by 2. And if you multiply h by a, you get square root of 2 multiplied by a rational number. And the square root of 2 is the cube root of 2, no, square root of 3. Yes, cube root of 3 is an irrational number. So the area of this triangle is irrational. So you see, you cannot draw an equilateral triangle on the screen of the computer. So I have a question for you. What are the regular polygons that you can try to draw on the computer? The equilateral triangle you cannot, the square you can, and what are the regular polygons that you can draw? So I leave it to you. Now I would like to explain to you how to draw a triangle which is almost equilateral. So we cannot draw a triangle which is really equilateral, but to have one which is almost equilateral. I propose the following solution. You need to have this summit which are on the grid, and so you have the length which is a, this will be b, and therefore, because this is a square, you will have a minus b, b, and a. And now, if it were an equilateral triangle, it would mean that this c is the same as the d, which is here. And you look at the equation it gives. We have c squared equal a squared plus b squared. This is this rectangle triangle. You have d squared, which is 2a minus b squared. It comes from this triangle, which is here. And so if c were equal to d, we would have a squared plus b squared equal 4ab. And this would mean a over b is 2 plus square root of 3. This is again the proof of what I explained before, that a over b is an irrational number. And so if you want to have a triangle which is almost equilateral, you have to find numbers a and b such that A divided by B is very close to 2 the square root of 3. And so I give you the answer. This is given by a sequence of A and Bn, which is given as follows. We start with 1, 0, 4, 1, 15, 4, and so on. And you see that Dn square and Cn square will differ only by 1. So Cn will be very close to Dn. So this is the best way to construct triangles which are almost equilateral. The references for what I told you is on a paper by Conway, The Power of Mathematics, where there are the pictures which are here, and the same are given in Jean-Paul Delahaye, and there is a YouTube movie, video, which is in Mathology. It's quite a nice video, which I recommend. If you prefer algebra to geometry, you can write exactly what I explained before without geometry, but using algebra. You assume that square root of d is n over n when d is a positive integer, and this will work with any positive integer which is not the square of an integer. And then we can prove that it is not the square of a rational number. And I give two proofs for that. Because the square root of d is not an integer, we can find an integer between square root of d minus 1 and square root of d, strictly between. And then, by taking n prime and n prime, which will be less than n and n, you find another solution, square root of d equal n prime over n prime, where n prime and n prime are less than n and n. So again, by infinite descent of Fermat, if you like, we get a contradiction. And this is one proof, and there is another proof. Instead of taking k less than square root of d, we can take n greater than square root of d, and another argument gives the same. And if you look at the case d equal 2 and 3, this corresponds to the images which I showed before. But this works in general. If you take a rectangle with proportion square root of d, like the A4 paper, then you can split this rectangle in two rectangles with the proportion 1 plus square root of d. 1 square plus 2 rectangles with proportion 1 plus square root of d. So you start with this A4 paper, and what I did before was to split it in two parts here. This is not what I do now. What I do is that I split it in 1 square. So 1 square, you fold it like this. Okay, I will take the other sheet. It will be easier. So you fold it like this. So when you fold it like this, you have 1 square. And so what you do is that you remove this square. This was the light blue. And so you have a rectangle. But the rectangle is rather, you see that it does not have the right proportion. You have a rectangle like this. So what you do with this rectangle is that you remove 2 squares, because now you have the space for removing 2 squares. So I remove 1 square, and then I remove another square. Okay, so I have a tiny rectangle which is left, and so I remove them, and so now I have a tiny rectangle which is like this. And this tiny rectangle, you can check that it has the same proportion as the previous one, which was very long. And then you can remove, maybe I did not remove them very precisely, but you can remove again 2 rectangles. So when you do that, you have 1 square plus 2 rectangles. Now you remove these 2 rectangles, you have again 2 squares plus a tiny rectangle. And you can continue for a while. If you do it with an A4 paper, you cannot do it infinitely often, especially because it's too difficult when you have a very small piece of paper. But if you start with a piece of paper which is exactly A4, which means 297 centimeters over 210, the proportion is 99 divided by 70. And what you do is that you write 91 divided by 70 equal, so this is the square root of 2. It is a number which starts with 1 or 0.4, something like this. So you can write it 1 plus 29 divided by 70. So you remove this, and then you look at this rectangle that you have here. The sides, the sides of this rectangle. So the long one was 297, and this one was 210. So you look at the one that you have here, and the proportion will be 29 and 70. So the 70 comes from this one, and this is the 29. And so you look at this rectangle here, but the proportion I always took the large side divided by the small one. So the proportion is not 29 divided by 70, but 70 divided by 29. And it turns out that it is 2 plus 12 divided by 29. So this is the 2 which is here, and then we have a small rectangle, which we write 2 plus 5 divided by 12. 12 divided by 5 is 2 plus 2 divided by 5. 5 divided by 2 is 2 plus 1/2, and then it stops. And it's clear that if you do that with a rectangle where the sides are integers, it will stop, because again you have a sequence of integers which are positive and decreasing. So this is the continuous fraction of square root of 2. We have square root of 2 equal 1 plus 1 over 1 plus square root of 2. We replace this square root of 2 by the formula, which is here. And then we have 1, 2, 2, 2. And so we write it 1, 2 with a bar, which means that this is the infinite continuous fraction of square root of 2. And if you start with any rational number, the continuous fraction will stop, and therefore square root of 2 is not a rational number. So this is why I told you there are several proofs of the irrationality of square root of 2. So I discussed the continuous fraction. There are other ways of studying square root of 2, in particular to write the decimal expansion. And this decimal expansion, we can work it and get many digits. I wrote a few digits to start with. And we know that the digits will continue infinitely often. We know that it will never become periodic. It's not true that after some time you will get the same pattern. It will always be different. But what else can be said on the decimal expansion of square root of 2?
You said that there is no repetition of patterns.
There is no pattern of repetition. Yes, repetition like ABCD, ABCD, ABCD. There is no period starting from one point onwards.
Not even of length 2.
Yes, we know that there is no so it is not ultimately periodic. It's not periodic, but not ultimately periodic, which means that after some pattern which could be anything, it is not true that it should repeat the same pattern infinity of them.
I think in the case of pi, there is a repetition.
We do not know for pi. Well, no, we know also for any irrational number, it is not periodic.
It's not repeated.
There is no period, yes. Instead of the decimal expansion, you can look at the binary expansion, and you have a sequence of 0 and 1. And the question is, what can we say about this sequence? Again, it's not periodic, which means that, for example, it will not continue with 0 after a while, it will not continue with 1, it will not continue with 1, 0, 1, 0, and so on. But what else can be said? This problem, well, give rise to a study of the decimal expansion of square root of 2. In 1951, 1,000 decimal digits were computed, and in 1967, 14,000 were computed, and 1 million in 1971. But now we know a lot of decimals. The number is maybe it has been enlarged after 1997, but it was 10 to the 9 digits, decimal expansion. And some people ask me what is the use of that, and one answer is that this was used to compute the decimal expansion of the number pi. Of course, the next question is why do you want to compute so many digits to pi, but I will not discuss that. The question of the decimal expansion of square root of 2 was studied by Émile Borel in 1950. So on the decimal digit of square root of 2 and several problems of probability, but he was already interested in similar problems in 1909. So he has been interested to this question for a long time, and he made some suggestion, which is that the decimal digit or the binary digit or in any basis, they should behave like a random sequence. What does it mean? It means that if you take any digit, it should occur infinitely often. Any pair of digits should occur infinitely often, and so on. And not only infinitely often, but also with the right proportion, right probability. This is where probability comes into the picture. And this was a question which was asked 70 years ago, and we know very few things. For example, if you take square root of 2 and if you take one digit, 7 for example, we cannot say, we can prove that 7 occurs infinitely often. It could be that after a while there is no 7. But this is not what Borel suggests. But instead of 7, I can take any digit. We do not know whether this digit occurs infinitely often. But instead of basis 10, I can take any basis, 2, 3, 4, and so on. And instead of square root of 2, I can take any algebraic number, any root of the polynomial with integer coefficient. And the answer is that we know nothing, which is we do not know any example of any rational number, any digit, any basis, where we can answer the question of Borel. The only thing that we can do is that if we take basis 2, the binary digits, each digit occurs infinitely often. Otherwise, it would be periodic. But apart from that, we know nothing. So you see that it is a domain where there is a lot of things which remain to be answered. Okay, I spoke a long time on square root of 2. I should speak on other numbers, and in particular the golden ratio. And I will start with a nice rectangle. And I need to give a definition of what is a nice rectangle. And my definition is the following. A nice rectangle is a rectangle such that if you remove a square, you get a smaller rectangle, which is a nice rectangle. And I like to give this definition because I use the word nice rectangle inside the definition, but it makes sense. Because it means that the small rectangle will have the same proportion as the large one. So if the large rectangle had the size 1 and 5, the square will have the size 1 and 1, and the small rectangle will have the sizes which are 1 and 5 minus 1. To say that the large one and the small one has the same proportion means that 5 divided by 1 is the same as 1 divided by 5 minus 1, which is 5 squared equals 5 plus 1. And there is a unique positive real number 5 which satisfies this, and this is the golden ratio, 1 plus square root of 5 divided by 2. And now, because of 5 equals 1 plus 1 over 5, you get the continuous fraction of 5, which has only once, and it is infinite, which means that if you split this sheet of paper with the size which the proportion which is 5, you will be able to continue infinitely often. And since you cannot continue infinitely often, it proves that 5 is an irrational number, and therefore square root of 5 is also an irrational number. So if you start with 1 and 5, when you split the golden rectangle into a square plus a small rectangle, the small rectangle has the sizes which are 1 and 1/5, which means that you have shrinked the big one by a coefficient 5. And so if you continue the process, you will have a smaller rectangle where the sizes are 1/5 and 1/5 squared, and then 1/5 to the cube and so on. I would like to come a little bit to the number square root of 2, because there is something similar for the number square root of 2 as for the number 5. Let me explain you that if you take a pentagon, the diagonal of the pentagon of side 1 is the golden ratio. So I hope you see here you have a pentagon which is start here 1, this, and this. Maybe I will use the whiteboard to draw this picture. So the small pentagon is this one. What I will do is that I will enlarge the small pentagon by a coefficient 5. And so I will have another pentagon where the side is 5. What is 5? It is the diagonal of the small pentagon. So you see, I write it 5 and we will see that it is the golden ratio. So I have 5 here, and I take a pentagon which has the 5 sizes which are 5, 5, 5, and the same here. And the diagonal of the big pentagon, we will check that it is 1 plus 5. But since it was obtained from the small pentagon by a coefficient, multiplicative coefficient 5, it means that 1 plus 5 is 5 squared. And this is the golden ratio. So, okay, maybe I leave it as an exercise. It's not difficult to check. What you have to check is that this big pentagon here, this 5 here is on the straight line with 1, so you have to look at the angles which are here. You have to compute this angle here, which is 3 pi over 5. This one has the angle is pi over 5, and then you see that this is on the straight line, and this is also on the straight line. So it's not difficult to check that this is the reality. If you want me to give the proof, I can give it at the end of the talk. It's similar with the square root of 2. If you take an regular octagon, so 8 sides, where the side here is 1, then this is 1, this is 1. This one, each of the sizes will be square root of 2 divided by 2. Because a squared plus b squared is equal to c squared. C is 1, and so a and b are square root of 2 divided by 2. And so this is 1, and this is 1 plus square root of 2 over 2, plus square root of 2 over 2. So the diagonal of the octagon is 1 plus square root of 2. It's something which occurs often for the two numbers. Square root of 2 occurs with symmetry, which occurs with powers of 2. Here it's 8. And the golden ratio occurs with symmetry, which are related to square root of 5, with 5. So it's 5 sides. The number 5 satisfies 5 squared equals 1 plus 5. We can write it as 5 is the square root of 1 plus 5, and this 5 we can replace it by the formula. So we have the square root of 1 plus square root of 1 plus 5, and we can continue. And we have the so-called nested roots that you may have seen somewhere. If you have seen them, it's very likely that it is in the work of Rajagiri, when he wrote to the Journal of the Indian Mathematical Society in 1912, he solved the problem, which was to compute this nested root and this one. This is the root of 1 plus 2 square root of 1 plus 3 square root of 1, and he found the answer, which is 3. And here, if you have the sequence, so here you have 2, 3, 4, and here 6, 7, 8, 9, then this nested root has the value 4. It's a very nice exercise. And we can compare with the square root of 2. If you write 1 plus square root of 2 squared is 1 plus 2 square root, 1 plus square root of 2. This 1 plus square root of 2 you can replace by the root, and you find a nested root, which has the value 1 plus square root of 2. So again, we see some similarity between square root of 2 and the golden ratio. Now, after the square root of 2 and the golden ratio, I need to speak on the Fibonacci sequence. And the Fibonacci sequence occurs in some problems of population. And instead of looking at the descendant, I look at the ancestors. How many ancestors do we have? If you have the white one, you have a father and a mother, and the father has a father and a mother, and the mother has a father and a mother. And the same when you go backwards to your ancestors, and you see that the number of ancestors that you have give the sequence 1, 2, 4, 8, 16, which is the sequence defined by u0 equal 1, this is u, and un plus 1 is 2un. So each time we multiply by 2, we have a sequence of powers of 2. This looks like a universal property, which is not completely true, because if you go backwards in the time, then the number is not, the population is not increasing that way. And if you look at 1,000 years ago, the population is not 2 to the power 1,000. So this is a good approximation, not more. But also, it's not a complete universal property, because if you look at the bees genealogy, the male honeybees are born from unfertilized egg, which means that the male have one mother, but no father. And the female honeybees are born from fertilized eggs, so the female has a father and a mother. So this father has only a mother, and this mother has a father and a mother. This mother has a father and a mother. This father has a mother, and this lady has a father and a mother. So you see that the number of ancestors does not follow the geometric series law. What is the number? You can compute the number of bees. You have 1, 1, 2, 3, 5. You can count the number of females. You have 0, 1, 1, 2, 3. And each time the rule is the same. You get a number by adding the two previous ones. un plus 2 is un plus 1 plus un. And so this is what you obtain for the genealogy of the bees. You start from the male, you have a mother, a male and a mother, and then it continues like this. And this is the rule starting with 1 and 1. One yourself and one father. Well, not yourself, but the bee. This sequence was known until 1850 or 70 with the name of Lamé series. What Lamé proved with this series is that this is the sequence of integers for which, if you take the quotient of two consecutive such integers, for example 233 divided by 144, when you write the Euclidean division, you have the longest number of steps. And so this was the theorem of Lamé, this is still the theorem of Lamé, and because of that, this sequence was defined as the Lamé series, which started like that. But in a trip to Italy in 1876, Edouard Lucas found them in a copy of the Fibonacci of Leonardo da Pisa, and after that it was called the Fibonacci sequence, because this was the name of Leonardo Pisano, Fibonacci, the son of Fibonacci. So the Fibonacci sequence is defined by f0 equals 0, f1 equals 1, fn plus 2 is fn plus 1 plus fn. And this sequence was introduced by Fibonacci, who was the son of Fibonacci. He was traveling around the Mediterranean, and he learned the technique of Rajagiri, and he published the Fibonacci in 1202. Whenever you have a sequence of integers, I advise you to have a look at the Encyclopedia of Integer Sequences, and this encyclopedia contains the Fibonacci sequence, so you have a lot of information on this sequence, on this encyclopedia. In particular, Sloan, on his encyclopedia,
gives some comments on this sequence, and he said that it refers to a book by Knut, who writes that this sequence was known by some Indian mathematician and scholars, Gopala and Hemachandra, and he said that sometimes they are called Hemachandra numbers. And I will explain how they occur in the musical patterns. The way that Fibonacci introduces this sequence is by giving the following problem. A newly born pair of rabbits, a male and a female, are put in a field. Rabbits are able to mate at the age of 1 month, so that at the end of its 2nd month, the female can produce another pair of rabbits. It's important that at the end of the 2nd month, rabbits never die and the mating pair always produces. And he asked how many pairs will they be in 1 year. And the answer is the 12th Fibonacci number, which is 144. And the sequence starts with 1, 1, 2, 3, 5, 8. And the 12th number is 140. So this is the modelization of the population by Fibonacci. He starts with a young pair for the 1st month. At the end of the 2nd month, the pair is adult and gives rise in the 3rd month to a young pair. Then the old pair always stays alive. The young pair becomes adult and then gives rise to a new pair. And so this gives rise to the sequence of Fibonacci. If you compare with the growth which I mentioned before for the genealogy, you can say that it's a modelization of a population of mice where they didn't wait the 3rd month, but they reproduce every month. And so the 1st month you have 1 pair, the 2nd month 2, and then 4, 8, and this is the exponential sequence, which can be explained in a similar way as the Fibonacci sequence. I introduced some squares at the beginning of my talk for square root of 2. We can also put some squares for the Fibonacci sequence as follows. We start with 1 square, which has size 1. And next to it, we put 1 square of the same size. So you have a rectangle. And this rectangle, it has size 1 and 2. You put a square, which has size 2, next to it, and you have a longer rectangle. The next rectangle would have size 3, and then 5, 8. And like this, you get the sequence of Fibonacci squares where the sizes are given by the Fibonacci numbers. This is the geometric construction of the Fibonacci sequence with 1, 1, 2, 3, 5, 8. And this sequence can be completed by drawing a spiral, starting with the first square, 1, 1, 2, 3, and so on. And this kind of spiral occurs in nature, in the ammonite, the Nautilus shape, and you find something which is very similar to the Fibonacci sequence. The Fibonacci sequence numbers occur in nature. This is called the phyllotaxy. Phyllotaxy is the study of the position of leaves on a stem and the reason for them. And we find Fibonacci numbers in nature when we count the number of petals of flowers, daisies, sunflowers, aster, chicory, aceracea. And we find them also in pine cones, pineapple, Romanesco cauliflowers, cactus. So you have here a few pictures on leaf arrangement where you find the number of leaves which follow the Fibonacci sequence, and also the way that the leaves are put on the stem, which is here. They turn around, and the Fibonacci numbers are related here. And it is the same here. If you look at the spirals that you have here or there, you find the Fibonacci sequence of numbers in these spirals. The same in this one with the cauliflowers, for example, the cactus. Phyllotaxy was studied by Kepler in 1611, and he studied the dodecahedron and the icosahedron, and he found some symmetry of order 5 in these flowers. which is something interesting for the people who study crystallography, because we know that there is no symmetry of order 5 when you bake the planet. But they occur in nature, and there are some papers on this topic. A book which is quite interesting is Pattern in Nature by Peter Stevens, and another book is on growth and forms by Sampson. And they include a lot of concrete information on occurrence of Fibonacci numbers in nature. The question which is often asked is why are there so many occurrences of Fibonacci numbers and the golden ratio in nature? And one explanation may be the following. Fibonacci numbers and the golden ratio have a small Kolmogorov complexity, which means that the program to compute them is very easy. There are just very few lines of code to write, and in nature it is expected that what occurs is more often what is simple from the Kolmogorov complexity than what is complicated to produce using codes. And if you look at the Sierpinski triangle, which is this one, or this kind of patterns, it looks complicated. But to produce them can be done with a code which is very small. And this may be the reason for which it occurs. Maybe I will finish if I have just a few minutes. Is it okay?
Yeah.
How much? Half an hour? 2 hours?
5 minutes.
5 minutes. Okay, so I will just give a few examples where Fibonacci numbers occur. The first one is reflection of a ray of light. You have 3 parallel sheets of glass here, and you have a ray which crosses the first one, and then it has a choice. Either it crosses completely, or it reflects on the glass, the sheet which is in the middle, or it reflects on the other one. And after a number of reflections, it goes out. You see, for example, it can go here, it reflects on the sheet in the middle, it goes up, it goes down, and then it goes out. And so we ask how many different paths are there with the ray going out of the system after n reflection. If there is no reflection, then there is one path. If there is one reflection, the reflection can be on the ray in the middle, on the sheet in the middle, or on the sheet which is below. So there are 2 possible paths, and each time the ray will go up on the top. If there are 2 reflections, the 2 reflections may be in the middle and on the top, or on the below and in the middle, or below and then on the top. So you have 3 possibilities, and each time, of course, the ray goes down at the end. And then for 3 reflections, you have these possibilities, and in general, you have the Fibonacci sequence. We start with 1, 2, 3, 5. So this is an occurrence of the Fibonacci sequence. Another one is the level of energy of an electron of an atom of hydrogen. The atom can have 3 levels of energy. If it does not move, then the level is 0, and it can have the level 1 or 2, neither below 0, neither more than 2. And at each step, it gains and loses some level of energy, 1 or 2. But it doesn't go down below 0, nor above 2. And we add a number of different possible scenarios for this electron after n steps. So the first step, there is nothing to be said. There is a state level which is 0. And then, after 1 step, the level can have, it starts from 0, it can go to the level 1 or to the level 2. So there are 2 possibilities. For the next possibility, you start from 0, 1 or from 0, 2, because this was the 2 scenario. If you are in 0, 1, you have to go down to 0. If you are in 0, 2, you have to go down. You go down either to 1 or to 0. And so on. So the numbers that you find is 1, 2, 3, 5, and again the Fibonacci number. And I will probably end with the repeat patterns, which were mentioned in the online encyclopedia of intelligent sequences of Sloan, where he said that this was the Fibonacci sequence appeared in Indian mathematics in connection with Sanskrit prosody, and it was introduced by Pigala, Viramuka, Gopala, and Eva Chandra. They studied rhythmic patterns that are formed by concatenating one bit note and double bit notes. So you do not have a single bit note. The double bit note, there are two of them. And so you ask, so the one bit note, you can say that it is T in the Morse alphabet, and the double bit note will be Tata in Morse. So if you have one bit, there is just one pattern, which is T. If you have two bits, you have two patterns. One is T, so it corresponds to two patterns, and the other is no, TT is so one, two bits, and then you have the double bit note. So you have two patterns. For 3 bits, you can have TTT, T pattern, or pattern T. This gives 3 possibilities. And for 4 bits, you can have unities. Whenever you have a double bit note, it counts for one item, and so you have tata TT, or T tata T, TT tata, or tata tata. And altogether, you find that the number of patterns is 1, 2, 3, 5, and it is the Fibonacci sequence which occurs here. So there are many other things to be said on this sequence and the connection between the Fibonacci sequence and the golden ratio, but probably it's time that I stop. You can get more information on the rest of my talk by downloading my file on my website. Thank you very much.
Any comments or suggestions?
Randomly a number is, can you check whether it is a Fibonacci number or not?
Whether it is?
Arbitrarily, suppose I choose a number, is it possible to check whether it is a Fibonacci number or not?
Whether it is I did not understand the way.
So I choose a number.
Is it possible to check whether it is
Fibonacci number
a Fibonacci number? It depends on the size of your number. If you give a number with some number of digits, which is 1000, maybe a little bit difficult. But the way to compute it is to know what is the size of your number, and you solve the equation. So let the number be k. What you do is that you take the logarithm of k, so it decreases the size quite dramatically, and you divide by the logarithm of 5, which is the golden ratio. So you have a number like this, and you look whether it is an integer or not. And the point is that there is a coefficient square root of 5 which comes into the picture. You have to divide by square root of 5. But apart from that, what happens is that the Fibonacci numbers are the numbers which are the closest to 5 to the n divided by square root of 5. So to compute the Fibonacci number, if you want to have the Fibonacci with a very large exponent n, then you do not have to compute all the Fibonacci numbers between that. You compute 5 to the n, and you divide by square root of 5. And so, for your question, indeed, there is an algorithm which is a polynomial, which is good because this is what we expect. There is a polynomial algorithm to check whether the given integer is a Fibonacci number.
If there are no other questions, just thank Professor Michel for his wonderful, simple, and informative talk. Thank you. As a token of our gratitude and respect, I request Professor Michel to accept a memento, and I invite our principal, Professor Srijit, to give the memento to Professor Michel. thank the management, our director, Reverend Fathers, our principal, Dr. P.S. Srijit, all the members of the staff, HODs, and all the participants for your attendance and conduct of this distinguished lecture. Thank you. We will assemble for a photo session just outside.